Types of formulas. Formulas are classified into the following categories based on the purpose they are used for. Algebra formulas. Algebra formulas are used in equations, inequalities, wordy problems, etc. We consider as formulas all identities that are expressed in the form of properties. The 8 basic algebraic identities, all properties of indices, roots, ratios, and proportion, the formula of percentage, etc., are all examples of algebraic formulas. We have explained all of them in the previous chapters. Other algebraic formulas we will see in the next chapters include the quadratic formula, arithmetic and geometric series formulas by which we calculate the value of nth term or the sum of n terms of such series, and so on. Example 1. The sides of a cube are constructed using bars that are made of two different materials, A and B. Write a formula that gives the spatial relationship between the two materials present in the cube if the ratio between the lengths of A and B is the same everywhere. Solution 1. To consider the spatial relationship between the two materials, we must find a formula that shows how these quantities are combined in the volume of the cube. Since the two materials are combined at the same ratio, we have A plus B equals constant, as the cube sides have the same length. From geometry we know that the volume of a cube is calculated by raising the side length to the third power. Hence, we have the following as shown on screen. This expression represents one of the 8 special algebraic identities, cube of a sum. When expanded, it becomes the following as shown on screen. Hence, the expression for volume in terms of materials A and B for such a cube is shown in the following on screen. Geometry formulas. Geometry is the branch that probably contains the largest number of formulas, from perimeter and area of various shapes to volume of solid objects, from trigonometry to polygons, from plane to space geometry, and so on. We will deal with all these fields and others in the upcoming chapters of this course. Here, we are going to illustrate the concept of geometric formulas with a simple example. Example 2. A. Given the formula of the circumference of a circle, c equals 2 pi r, where r is the radius and pi is a constant, pi approximately equal to 3.14, and that of the area of a circle, a equals pi r squared. Find the formula for the total area of a thin and hollow cylinder. If the height h is known, we have the following as shown on screen. B. The cylinder is melted down to produce a sphere with the same material. The sphere is also thin and hollow. What is the r over r ratio if r is the base radius of cylinder and r is the radius of the sphere? Take the height h of cylinder as twice the base radius. The area of sphere is calculated by the formula as equals 4 pi r squared. Solution 2. A. A cylinder is made by two identical circles called bases, and one lateral face that is not plane but it is instead curved according to the circle's, bases, shape. The cylinder's opening is shown in the following on screen. From the openings shown previously, it is clear that lateral face is a rectangle, where the length L corresponds to the circumference of the circle, base, and width W corresponds to the cylinder's height. Therefore, given that the area of a rectangle is the product of its length and height, we can write for the total surface area of the cylinder. We have the following shown on screen. B. Since both solid shapes are thin and hollow, they have the same surface area. Therefore, we can write the following shown on screen. Since in the specific case h equals 2r, we obtain the following as shown on screen. Physics formulas. Physics is another field of science that contains a very large number of formulas. From kinematics to dynamics, from work and energy to momentum and impulse, from electricity to magnetism and electromagnetism, from optics to modern physics, etc. All these sub-branches of physics contain in their theory many formulas each. Let's consider an example in this regard. Example 3. Find the formula for the equivalent resistance R of two resistors R1 and R2 connected in parallel in the same electric circuit supplied by a source of potential difference, voltage, alpha V. Take into account the Ohm's law alpha V equals IR, where I is the current flowing through the circuit. To understand how current behaves in a parallel combination of resistors, use the analogy of water when splits in two separate branches. In addition, make use of the fact that the potential difference in a parallel branch is equal across each resistor. In absence of other resistors in the circuit, it is equal to the potential difference at the source, battery. We have the following shown on screen. Solution 3. The current I divides in two parts, I1 and I2, one for each parallel branch, like water in a river that divides in two different streams. Giving that the potential difference is the same across each resistor, alpha V1 equals alpha V2 equals alpha V, we can write based on the Ohm's law. We have the following shown on screen. Simplifying alpha V from both sides yields, we have the following shown on screen. This is the formula for the equivalent resistance of a parallel combination of two resistors. Chemistry formulas, compounds. Chemistry is also a branch of science that contains many formulas, where the most notorious are the molecular formula that show how atoms are combined in molecules, stoichiometric formulas that are mostly based on formula mass, i.e. in the sum of the atomic weights of each atom present in the molecule of the substance, element percentages formulas in compounds, etc. As illustration, we will take here an example with element percentages in compounds. Example 4. A compound made from two substances A and B has the following formula. We have the following as shown on screen. Where meters, B, equals 2.7 meters, A. If the original mass of the compound is 74 grams, how much from the substance A must be added in the compound to obtain a new compound where meters, B, equals 2 meters, A, without changing the amount of B? Solution 4. Let's denote by X the extra amount we must add to A in order to obtain the new compound. We have the following as shown on screen. We have the following as shown on screen. Hence, we have the following as shown on screen. When adding X gram from substance A in the compound, we will obtain meters, B, equals 2 meters, A plus X. Thus, since meters, B, does not change, we will have the following as shown on screen. Therefore, we must add 7 grams from the substance A in the compound to obtain the new ratio. Another situation that requires the use of formulas in chemistry involves the calculation of the percentage composition of an element in a compound. Thus, if we have a compound of generic formula A, X, B, Y, C, Z, the total masses per mole of A, B, and C are X, Ma, Y, Mb, and Z, Mc respectively. Thus, the mass percentage composition of element A in the compound is shown in the following on screen. For example, percent composition of hydrogen, H2, in sulfuric acid, H2SO4, giving that molar mass of hydrogen is 1.008 U, that of oxygen is 15.999 U, and molar mass of sulfur is 32.07 U. U is an abbreviation for atomic mass unit. We have the following as shown on screen. Spreadsheet formulas. A spreadsheet formula is an equation that performs a calculation on the numbers, functions, and values of one or more cells. A formula is associated with a cell or a cell range. In the formula bar, we must write that equal to sign first, then the name of formula. Then we open the brackets where the name of the first and the last cell separated by a semicolon are written. After closing the brackets, we click on the cell in which we want the result to appear. Then we press enter and the result appears in the designed cell. Example 5. The student scores for 3 classes in a math exam are shown in the table IN. The following extracted from an Excel spreadsheet. We have the following shown on screen. A. Which class had the best average score in the exam? B. What is the average score of all students? Solution 5. A. We have to calculate the average score for each class separately and compare the values obtained. In Excel, there is a function that has a formula called average, which we can use to avoid manual calculations. We write equals average, B4, B23, equals average, D4, D23, and average, F4, F23, in the formula bar, and the results obtained we can insert, for example, in B25, D25 and F25 cells respectively, as shown in the following on screen. This done, we obtain the results 51.5, 60.3 and 60.65 respectively. Hence, comparing these average scores, it is evident that the class Z had the highest score, 60.65 points, then it comes the class Y, 60.3 points, and the class X, which had the lowest average score, 51.15 points. B. To find the average score of all students, we can write in the formula bar the following command, equals average, B25, C25, F25. We can insert the result, 57.3667, in another cell, for example in H25, as shown in the figure N the following on screen. This procedure avoids long manual calculations that may also result in errors. Banking formulas, interest. We explained in tutorial 5.4 the concepts of simple and compound interest. Thus, if the principal, original amount deposited or borrowed, if P, and the simple interest rate is R, the formula used for calculating the total amount A, T, to be received or paid after a period T, this is shown in the following on screen. For example, if a customer deposits $20,000 in a bank, P equals 20,000. That applies simple annual interest rates of 4%, we write it as a decimal, i.e. R equals 4% equals 0.04, the amount this customer will have in her savings account after 6 years of deposit, T equals 6. We have the following as shown on screen. Therefore, the customer will have $24,800 in her saving account after 6 years of deposit. Likewise, if a customer makes a $25,000 deposit, P equals 25,000, in his savings account in a bank that applies 2.5% interest rates, R equals 2.4% equals 0.024, compounded twice in a year, N equals 3. He will have in his account after 4 years of deposit, T equals 4, we have the following as shown on screen. Hence, the customer will have $27,507.50 in his savings account after 4 years. Example 6. A customer wants to deposit $5,000 in a bank for 3 years. He has 2 saving accounts, one in the bank A that offers 4% simple annual interest rates and the other in the bank B, that offers 2% interest rates compound twice in a year. What bank do you suggest that she choose? Solution 6. We must calculate the amounts A, SI, and A, CI, and compare them, where SI stands for simple interest, while CI for the compound interest. Obviously, we must use the simple interest formula for the bank A and compound interest formula for the bank B. We have the following clues, we have the following as shown on screen. The amount the customer will have in her savings account in the bank A, after 3 years of deposit is shown in the following on screen. The amount the customer will have in her savings account in the bank B, after 3 years of deposit, is shown in the following on screen. Thus, the customer will earn more if she deposits her savings in the bank A. Engineering formulas. Engineering is a branch of science that consists in the application in practice of science and math to solve problems. Engineers figure out how things work and find practical uses for scientific discoveries. In this sense, engineering is the combination of math and other natural sciences. Calculations and formulas in engineering are usually more complicated than in physics or math. There are many engineering sub-branches, such as mechanical engineering, civil engineering, computer engineering, electrical engineering, etc. We will illustrate the use of formula with an example in mechanical engineering, which deals with structures construction. Example 7. What is the maximum weight of 1.200 meters long and 2.0 centimeters squared thick iron bar can hold when hooked vertically from the ceiling of a strong structure? The Young modulus E is a constant that represents the strength of material. For iron is 1011 N per meters squared, and it is calculated by dividing stress sigma, force over cross-sectional area, and strain epsilon, change in length over original length. The breaking point of iron, the maximum elongation allowed without breaking, is reached when an iron bar extends up to 1/600th of its original length. We have the following shown on screen. Solution 7. The force in the stress formula can be replaced with the weight W, as from physics it is known that weight is a kind of downward force. In addition, we must take into account the fact that the units of area change 100 by 100. Thus, 1 centimeters squared equals 10⁻4 meters squared. We have the following shown on screen. We obtain the following shown on screen. By rearranging the last formula, we obtain the following shown on screen. Hence, the maximum weight the iron bar can hold is shown in the following on screen. That is all for lesson 8.2.1. To continue this tutorial, please watch 8.2.2 Rearranging Formulas. Thank you for watching. Make sure to like and subscribe to keep up to date with new videos. For more information, calculators, and tutorials, please visit www.icalculator.info.